Okay, welcome back. I think I got my tech issues sorted out. What we're going to do is take a look at 6.3. We're going to finish up this first example real quick and then take a look at a second example. So this first example, we started with a second order differential equation that also had some heaviside function going on. We first interpreted it in terms of a mass on a spring system, a harmonic oscillator, and then we did some the Laplace transform method in order to get it to solve. And so after some work, we came up with this at the very bottom. And one of the things that we know that we can do is we can use partial fractions in our maple in order to kind of split this second fraction up a little bit. So that's what I'm going to do next. I'm going to kind of split this thing up and say, using parfrac, we see that 3 over s squared plus 1 times s squared plus 4, that can be written as the sum of two other fractions, which I'm going to pull up in maple here in a second. So thanks to a little bit of coding in maple, we can do a quick partial fractions conversion, and we can rewrite our one fraction as the sum of two fractions. So this is really 1 over s squared plus 1 minus 1 over s squared plus 4. So I'm going to write that down in my notes, and then we'll switch back over to the notes and continue finishing the problem. So I used my partial fractions, and I've got that, what it's written down, what's the equivalent to. So that means, kind of continuing, that the Laplace transform of the solution to this differential equation initial value problem is whatever s over s squared plus 4, and we kind of already know what that is. We talked about that. That's actually going to be a cosine function, plus 3, oh, nope, not 3, just e. I'm going to leave our exponential out front here. E to the negative 10t times 1 over s squared plus 1 minus 1 over s squared plus 4. And with a little bit of help from the Laplace transform tables, which I can kind of flip back over to, these both should look pretty familiar. Those are both going to be evidence of, where's my sine? There it is. Nope, sine. Where's sine? There's sine. Something looking like this. Sine of omega t, something like that. Yeah, where was I? Ah, there we go. That's what I'm looking for. This guy right here. So a little bit of playing around. We can also do this in maple and kind of check and see what we got. If you look on maple and we do an inverse Laplace of that whole thing, we find out that it's a cosine function, which is coming from that 1 over s squared plus 4. Oh, that's supposed to be plus. What's going on there? What did I do? That's really weird. Oh, that's s over s squared plus 4. Got it. Sorry. I'm doing something else here. So if we switch back over to our document, let me see if I can find it. There we go. A little bit of effort. We find out that our inverse Laplace, applying the inverse Laplace in here, I probably should make a note of that. Applying the inverse Laplace to that takes us to an actual solution for the initial value problem, which is going to be from this guy right here. That's going to be our cosine of 2t. Well, that's coming from here. And then what we have for the remainder here are actually two shifted switch situations, right? But they both happen at the exact same moment in time. In this case, they both happen at 10 seconds. So this is going to be plus u sub 10 t times, and then it's going to be the difference between these two turkeys here. And this guy right here is just the sine function, but it's going to be shifted by 1. So sine of t minus 10, or sorry, shifted by 10. And then the other guy is coming from this guy right here, which is that 2 squared in the bottom is telling us that it's going to be a sine of 2t, but we're going to throw a 1/2 in front of it, times sine of, oops, I didn't want to put that parentheses right there, too soon. This is going to be sine of 2 times t minus 10. And so what we have are the shifted switches coming from this first one right there, and then the second one right there. And so what does this suggest is going on in our solution curve? Well, it's saying it's going to behave like cosine of 2t the whole time, but then all of a sudden when t equals 10, we're going to get these 2 extra terms of sine functions. Now, it's worth noting that they have different periods. So we're going to start off with a kind of a standard cosine function, and then at t equals 10, we're going to see a significant change. So let's switch over to Maple and see if we can see what that looks like. So after a little bit of coding, I just did the inverse Laplace there, and this is what we got. And by taking a look at its graph from t equals 0 out to, say, 60 seconds, what we're seeing is over the first 10 seconds, it behaves just like a cosine of 2t, right? And then all of a sudden, at that moment, that's when the forcing function changes. It turns on this sinusoidal forcing function. And notice, what it produces is not a clean, singular sine wave or a cosine wave. It's kind of a mixture. It's a mixture because we have multiple periodic functions with different periods kind of happening at the same time. And so after t equals 10, we wind up with this pattern. And it continues that way forever because we have a periodic forcing function and a harmonic oscillator that doesn't have any damping. So that's worth noting. So let's take a look at the next problem on the in the section, another example. This next example actually has a whole lot of stuff going on, and it's worth kind of hitting the pause button to make sure you've read it and you've had a chance to think about it. So if you haven't had a chance to look it over, just hit the pause button right now and take a look at it. I'll continue in a second with sort of explaining the context, but it's worth paying attention to. So it says we have a unit mass, which tells us something about the size of the mass, right? So this unit mass, that means mass equals whatever 1 unit of mass is. It's attached to a spring with a constant of 5. So spring with a constant of 5, that means the K value in my harmonic oscillator is 5. Sliding on a table with damping coefficient 2. So far, we've gotten a whole bunch of information that tells me something about my harmonic oscillator. And so all 3 of those pieces of information tell me that I have a harmonic oscillator that's going to behave like y prime, or excuse me, y double prime, because we've got unit mass, plus 2y prime, plus 5y. And you could say that equals 0. That would be my, if there were no forcing function. But in actuality, it's not that it equals 0, it's that it equals some forcing function. And that forcing function hopefully gets described later on. We'll try to make some sense out of it. And so notice it says at t equals 0, the mass is released from rest at position of y equals 0. So notice we have our table for any time less than 7 seconds. Our table is kind of propped up. So if it gets released from rest, you can imagine it's going to slide down the slope of the table. It's just going to go and sort of bounce down here because it's from rest of the equilibrium position for the harmonic oscillator. So the table's tilted, so gravity produces a force of 5 units stretching the spring. So I'm going to use a slightly different color here and say the mass is released and we wind up with a force of 5 units stretching the spring. But that only happens when t is less than 7. So that means before 7 seconds we have a force of 5. So it would be equal to 5, but then it turns off at 7 seconds. So what I need to do is multiply it by some switching function that turns things off. And if you remember from 6.2, the switching function that we're going to use is going to be 1 minus the Heaviside function at 7 seconds. So this turns it off at 7 seconds. So my forcing function is just a constant force of 5 until 7 seconds, and that's when we kind of pull the table back down so that it's flat, and then there's no forcing function in the horizontal direction. So this is the harmonic oscillator that we're dealing with. The other information that we need to know is what are the initial conditions that we're facing. So at t equals 0, the mass is released from rest at y equals 0. So that means y prime of 0 equals 0. From rest means no initial velocity. And the other thing that we know is y of 0 equals 0, because we didn't move the mass at all. We just kind of released it from its equilibrium position. So what we need to do is, given our harmonic oscillator equation, given our initial conditions, we need to solve this IVP. So our job is going to be to do that. So we have our harmonic oscillator equation set up. We know that solving this initial value problem really amounts to applying the Laplace transform. So our first step is going to be to apply, or to take, the Laplace transform of the equation, of the differential equation. And then we're going to solve for the Laplace transform of y. That's our goal for this first step, right? And so we're going to manipulate this. But first, we're going to apply the Laplace transform. So we've got Laplace transform of y double prime plus 2 times the Laplace transform of y prime plus 5 times the Laplace transform of y. And all that's going to be equal to the Laplace transform of our forcing function, which is 5 times 1 minus the Heaviside function switched on at t equals 7. So if you remember from the first example that we saw in this section, what we need to do is think of my Laplace transform of y double prime really as the Laplace transform of the derivative of the derivative. So you can recall that, just off to the side, I'll make a little note. Recall that y double prime is the same thing as the derivative of y prime. And that's what we're going to use in this first step. And along the way, we're going to be able to use our initial conditions, which are conveniently 0, which makes it a lot easier for us. So if you kind of break this apart, this is going to be s times the Laplace transform of y prime plus y prime of 0. That's all from our first, let me use little colors here. And we know that that's going to turn out to be 0, so that's no big deal for us. Sorry, 0. There we go. Plus 2 times the Laplace transform of y prime, which we know is 2 times s times the Laplace transform of y. Sorry, the 2 should be on the outside here. Plus, or not plus, I did it again. These are supposed to be minus. I know the formula, I just forget sometimes. That's minus y prime of 0, and that's minus y of 0. Now, fortunately for us, neither one of those makes a difference because they both turn out to be, thanks to our initial conditions, both turn out to be 0. So this one, all that's here, all of this stuff, is this stuff right here. And then, of course, we have plus 5 times the Laplace transform of y. The other side is we have to figure out what the Laplace transform of this is, but it's really two things. It's the Laplace transform of 5, a constant, minus 5 times the Laplace transform of u sub 7 of t. So breaking things apart as simply as possible, we've got one more step to do over here because it's the Laplace transform of y prime, And so we can break that down one more, and this becomes s times the Laplace transform of y minus my initial condition, y of 0. So all of that is coming from inside here, all that. And we also know that, of course, y of 0 is 0. Now, in a problem where the initial conditions are not both equal to 0, it's possible you could have a term here, and then another additional term here that winds up getting multiplied by s. So you got to keep up with the bookkeeping here. So this becomes plus 2s times the Laplace transform of y. This guy is 0, so it goes away. Plus 5 times the Laplace transform of y. The other side is Laplace transform of 5, if you remember. That's just going to be, Laplace transform of a constant is just that constant divided by s. And then the Laplace transform of the heaviside function is that 5 out front, negative 5 times, and then this thing is just e to the negative, whatever that subscript is, 7s over s. And so continuing, we wind up with s squared times the Laplace transform of y plus 2s times the Laplace transform of y plus 5 times the Laplace transform of y. And that's going to be equal to 5 over s minus 5 e to the minus 7s over s. Now, if you're paying attention, you might notice something kind of interesting. We wind up with, on this side, when we factor out the Laplace transform of y, we wind up with Laplace transform of y times a polynomial, which is s squared plus 2s plus 5. The other side is still all the same stuff. But take a look at that polynomial. Look carefully at that polynomial. It should look vaguely familiar if you go back and take a look at our original initial value problem. Look at that harmonic oscillator. This guy right here, that's essentially our characteristic polynomial. If we were doing, the eigenvalue method or, trying to use a lucky guess method, this would show up as our characteristic polynomial. And the only reason that it worked out the way this way is because our initial conditions were both 0. Because this term went away, that term went away, and this term went away. They were just zeros. So it turned out to appear as our characteristic polynomial, but it didn't have to. Given what our initial conditions are, it turned out to be that way. Otherwise, it might not have. So after all is said and done, we wind up with the Laplace transform of y is equal to all this stuff on this side divided by this polynomial. So I'm going to scoot these two together and make it 5 minus 5 e to the negative 7s all over s times s squared plus 2s plus 5. Now you might look at that and go, ugh, that's a mess. And it is. But what we need to be able to do in order to make sense of this is remember that we're trying to, at this point, say we have the Laplace transform of the actual solution. This thing right here is the Laplace transform of the solution, if only we could undo it. And so now, part 2 is we need to manipulate and apply the inverse Laplace. To get y of t, right? Our particular solution. Now, after a whole bunch of manipulation, there's a whole bunch of things that we can do here. The first thing is recognize we've actually got two fractions. There's the 5 over all this junk minus 5e to the negative 7s over all this junk. And then we could use partial fractions. We could kind of try to split this thing up. The hard work of this problem is actually the algebra of trying to manipulate that to make some sense of it. But let me show you what happens if we try to see what Maple gives us. I just typed in the Laplace transform inverse of our two terms by splitting up our fraction. And what you can see here is the first term is just 5 over s times all that big polynomial. The second one is 5e to the negative 7s over s times that polynomial. And after a little bit of work, Maple says, oh, okay, I think I got it. But take a look at our terms here. We've got 1 minus and then some exponential times a sum of periodics. And then, if you're looking really carefully, you can see that actually includes the imaginary number, I. And it's multiplied by, again, another I, and then e to an I power. So what this is telling us is we don't have a very simplified version of our solution. But we can still plot it and see what does this thing look like. And sure enough, if you plot it, you get something that looks like this. Now, what I'm going to do is I'm going to write down what the solution is equivalent to after a whole bunch of work. After a whole bunch of par fracking and manipulation, you can get this to turn into a real coefficient solution that looks like this. Now, in the old days, we used to spend, another 20 minutes or so walking through all of that. But I'm never going to make you do this by hand. I don't want you to do this by hand. I want you to use the computer, but I want you to be able to see where each one of these parts come from. And by the way, just as a reminder, we can always use Maple to just desolve this right out of the get-go. And Maple will apply it and wind up with exactly the solution that I just wrote down. So going back to what we see as the solution, it's worth kind of pulling out the pieces and kind of identifying what the pieces of this are. So you can notice these first two terms, these are just exponential decay times a trig term. And so this is the before t equals 7. Right? So if you want to know how this thing behaves before t equals 7, well, there you go. It's going to behave like this. And all of this, everything multiplied by this Heaviside function, all of this is off until t equals 7. There is one last little term here where you'd have a plus 1 that's on at first, and then it drops away down to nothing at t equals 7. So it's worth noting that that's the t equals, the before t equals 7 part. And then this, all this stuff through here and that, this is the after t equals 7 part. And it's worth noting that the after t equals 7 part still is exponential decay times trig functions. But then this 1 goes away. So before t equals 7, it's going to behave like this. All that junk underlined in orange plus 1. And then afterwards, it's all this plus this additional trig function. And so when we take a look at Maple to verify what that looks like as a graph, you can see that before t equals 7, right here, this thing behaves like, oh, it's an oscillator. It jumps up by 1. Its new equilibrium position, it looks like it's 1. And it's sort of heading towards that equilibrium. And then 7 seconds, we pull the book out, and the mass slides back down towards its original equilibrium position, which is y equals 0. So this thing looks like a mess, a complete mess. And sure enough, the graph is at least as much of a mess as the solution that we came up with just doing an inverse Laplace. For our purposes, I want you to be able to identify where each one of these kind of chunks comes from, in our solution. I want you to be able to use the procedure, show how the work of the Laplace Transform method happens, and then be able to comment on the graph. So that gets us to the end of this guy right here. And we can take a look at one more example at the end of section 6.3, and that'll be the last example for the course.